Welcome to the Energy InSites podcast, your source for the latest insights in deep retrofits, renewable energy, and energy conservation. And now let's get to today's insights. My guest today has spent his career making low carbon heating and cooling add up, both financially and technically. He's a professional engineer and the chief innovation officer at ThermaStor Solutions, where he designs Geoexchange and underground thermal storage systems that let building and whole districts electrify without overwhelming the grid. James Bererton, welcome to Energy Insights.
Thanks very much, Kevin. Glad to be here.
Yeah, so today's a special day. We're doing something we haven't done before on the podcast. We are going to do a doubleheader episode, back-to-back, 2 episodes, because it turns out James is a serial entrepreneur and he's doing good for the planet so seriously that he's got 2 businesses going. So we're going to cover each one independently, starting with ThermaStor Solutions. So James, thank you so much for joining us. I'm really excited to dive into the world of bore thermal energy storage, BTES. So,
right, yeah.
You've designed everything from net zero campuses to solar farms. Walk us through how you ended up specializing in storing energy underground.
Well, I should start at the beginning where I switched away from the evils of oil and gas and jumped into renewable energy. I lived about a block and a half away from a world-renowned Drake Landing solar community, and they did borehole thermal energy storage, and they heated 52 homes with only solar thermal energy. And so this is the 1.0 version, and where I got my feet wet in doing energy storage design and all of the renewables. I ended up switching my career because of that project, and met with international experts in the field and gained their knowledge, and now 20 some odd years later have advanced that knowledge and applied it. So Geoexchange, everyone's familiar with drilling boreholes in the ground and doing heating and cooling from that. But when you put those boreholes closer together and you try and store that energy from the summer to the winter or vice versa, then you have a different design dynamic. And so we've been competing those 2 designs, Geoexchange and borehole thermal energy storage. And I'm technology agnostic. I don't care what technology it is. I want to have something that's environmentally friendly, that's grid friendly, because we don't want to spend $40 billion upgrading our grid. And it has to be economic. So those are my primary constraints, whether I'm working at the scale of a 1 gigawatt data center or a single family residential design. You want to have all those things. So with borehole thermal energy storage, what we found was from the learnings at Drake Landing, if you could add heat pumps to that and you add the latest technology with a heat source like photovoltaic thermal, which I'll get into, it's a combination panel, does electrical generation and heating. You combine these technologies and you've come up with the lowest cost solution. And the solutions that we're putting out now in some tariff regions is competitive with chillers and boilers. So we can actually do a lower life cycle cost and sometimes even compete on a capital cost basis, which is really unheard of when you're trying to decarbonize. The real challenge.
You mean compared to natural gas fed systems?
To compete with natural gas. So we're
Wow.
I'm from Alberta out here. We have some of the cheapest natural gas in the country, if not in the world. So to try and do boilers here and then switch over to electrified, that's a really big challenge. And most times we can't beat it on a capital cost basis, but we try and beat it on a life cycle cost basis. So we have now found solutions that work even in Alberta, the toughest of markets. And in markets like Ontario, where they reward you for reducing your peak demand, or in Halifax, where they use it's $22 a gigajoule or MMBTU, about the same. It's very expensive. It's about 4 or 5 times the cost of Alberta. But in Alberta, our electricity is quite expensive and our gas is really cheap. So how do we solve that problem? We have to combine different technologies together in an efficient way. And so that's what I can talk about, and I can share some videos if you want.
Yeah, fantastic. And as part of our double header extravaganza, so we'll talk ThermaStor first, which is very commercial oriented, big scale, big projects, and then we're going to get into Ada Energy Solutions, which is more of your single family home, smaller scale residential stuff. So I'm really excited to cover the whole spectrum of topics today. In your opening statement, you mentioned a couple of things. You mentioned Drake Landing, and you mentioned Geoexchange. Now, I know what Geoexchange is, but it actually took me a minute to make the difference between geothermal and Geoexchange in the common language. So I think for the benefit of our audience, you're the first guest we've had who's been a Geoexchange person. I would love you to walk them through kind of some of those different definitions, as well as a little bit about Drake Landing, because I remember when that project happened. I was living in Calgary at the time. Super exciting thing, lots of lessons learned. Let's talk about that a little bit too.
For sure. Yeah. So geoexchange is when you drill boreholes in the ground and you access that constant earth temperature, which is the same as your annual average air temperature. So it's great if you want to do cooling. In Calgary, our annual average air temperature is somewhere around 5.5, 6 degrees Celsius. The earth is a little bit warmer because there's a geothermal gradient. And you take that temperature and either you're going to create cooling or you're going to create heating with it. So with the 6 degree source, I can create heating with a heat pump. I'll make it hot for the home in the winter, or in the summer, it's really easy to make cooling with that nice cold ground temperature. But the problem with Geoexchange is all summer long, I dump heat into the ground. Now it gets hot. It's hard for me to do cooling. At the beginning of heating, that's great. But at the end of the heating season, I've frozen the ground. The ground underneath those boreholes, around those boreholes, literally is frozen. We have to use glycol. And so we take that heat in and out of the ground, and it has to be balanced. So you've got your heat pump, it's connected to the earth, this great resource, but we're either heating it, making it too hot, or cooling it, making it too cold when we're trying to get heat out of it. And that's the challenge with Geoexchange. So to make that work on a building level, you have to have similar heating and cooling loads or similar energy into and out of the earth. To overcome that, we use borehole thermal energy storage.
Okay.
Go ahead.
Yeah, just making a distinction as well between sort of utility scale geothermal and then Geoexchange being sometimes a little more shallow. Like when I think of geothermal, I think of utility scale, very deep holes.
Well, we call that hot
megawatts. Huge multi-year undertakings, mega dollars. Whereas Geoexchange can be more of a shallow horizontal. Or are you referring to a
vertical boreholes,
relatively shallow but vertical?
That's right. And that would be what we call low enthalpy or low temperature Geoexchange. That's what I'm talking about. What you just mentioned is what we refer to as hot rock. So hot rock you have to have in a geologically active zone that's close to the surface. That's the magma coming up, and you can generate heat and power from that. We've got companies and specialists even in Alberta. Ever is one of them, and they do deep, like 2.5 kilometers deep boreholes, and they can generate power. But that is a different technology. It's excellent technology and should be explored further. And in fact, we work with them to store that energy they take out and store it near the surface in these bore fields, and then we can harness that energy when we need it. But what we're talking primarily is heating and cooling loads, trying to displace those. And what we found is this shallow, low temperature Geoexchange is the best way to do it. And then on top of that, we do this borehole thermal energy storage, which is like a version of Geoexchange, but we concentrate all the heat or cold in the middle of the field, and we do it in concentric rings, and the boreholes are closer together. But it's the same boreholes. We're in the 400 to 800 foot depth. It's very close to the surface. And then one of the tricks that ThermaCity Energy has is we have a specialized drilling rig that can go into existing buildings and drill beneath the parking structure. So now we can unlock retrofit of large existing buildings. And if you count how many buildings were built this year versus how many buildings exist, there's a lot more that exist at any given time.
Yeah, and so when you visualize your classic drilling rig that anyone's ever seen on an oil site, they have these huge towers that are whatever 50 feet high, let's say, maybe taller, to then have long pipes going into the ground to drill these oil wells. But obviously, in an existing building, you're not getting that thing in the parking garage. So you
No,
guys did an innovation there. Tell us about that.
so that innovation at ThermaCity Energy is our drill rig. So we call it the drill bot. And what it is again, it's a transfer of technology from the oil and gas world over to the heating and cooling space. And to drill in that height, we're talking 6'4" or 2.3 meters height. So what happens is we put the metal, instead of having sticks, you have what we call sticks, long rods of metal that rotate and drill into the earth. That's how you do a standard drilling rig. But for the coil and tubing, it's a metal pipe wrapped around, and I can show you a little image of it if I can try and share here. It's the visual's worth 1,000 words. Let's see if we can pull it up. So it looks like this, and it's patent pending, so we can't show you a very detailed version of it, but this is how it works. So the metal drill component is a big metal pipe on this wheel, this reel, and then it goes down into the ground, and the motor, the drill motor, is actually located below surface, and it goes down with that coil, and the coil is feeding the mud into the motor, and that it's actually driven by the same water and mud that is drilling the hole. So that's what turns the drill bit at the end of the motor down into the earth. And we can go continuously. It just rolls out into the hole, and then we roll it back up. And you can do that about 100, 120 times. And that's how we drill underneath the building.
You mean until you wear out the bits or something?
You wear out, so it's coiled up metal. That metal pipe will wear out, and eventually that would break or fatigue, and then you just get, what we do is our reel pops off, and we pop on a new reel, and away we go. We keep going.
Amazing. And so this is a Canadian innovation, or?
Yep. Canadian innovation. Our founder actually did this kind of work on a building with 3-foot drill rods. So in 2012, they did Cadillac Fairview out in Vancouver, and they went underneath the parking structure, and they drilled a Geoexchange field underneath it. This first one in the world that was done underneath an existing building, and they covered a big fraction of their energy, but they found 3 foot. So you got two guys trying to do 3 foot at a time, drilling these 400-foot boreholes.
Oh my goodness.
Yeah, it's here's the example of it. I'll show you a picture of that. Right.
Well, kudos to Cadillac Fairview for getting after it in 2012.
Yeah, that's way ahead of their time and ahead of the technology. So we had to invent new technology to be able to do what they did, only now economic, cheaper, faster, better. So you can see the little cover there, the manhole cover. Underneath that's the borehole, and then they pipe underneath the slab and then up to the ceiling. And that's exactly how we'll do it today. The only difference is we've got a drill rig that is fully automated, requires one man. He could even do it remotely, and it continuously drills, so it's quite a bit faster. And there's a whole process to it, because we want to keep all that space clean. So we have to clean the mud, we have to process the drill cuttings, and then put the water back in the hole.
Very clean.
So yeah, exactly.
Is it messy during the process, or is it fairly? You've got it all kind of self-contained.
All self-contained. All the drill mud gets pumped to the surface. It gets cleaned. The mud gets added back into the drill bot to go downhole. The cuttings get taken away in containers on trucks. So it's a whole process that is also part of our patent pending process. So that was done. They did a clean install then with these old technology stick rigs, but now we can do it with a much more advanced system.
And that looks like a mixed use, either residential, commercial, or office building of sort there in the picture.
Office building. Yeah, it's a class A office building profile.
So for a building like that, how many of those holes would you have scattered around the parking garage?
So the way I describe it today with our new technology, that's adding in the other learnings from Drake Landing, because we're not doing just Geoexchange, we're doing what we call geostorage. The best case we have is a 49-story apartment complex, so a multi-unit residential building. And within that footprint, we can cover 90% of the heating and cooling loads. with
Wow.
our technology. So that gives you an idea of what we would cover and how much of the space we'd need to meet that. But a 49-story tall building, so obviously with shorter buildings, we would only use a fraction of their footprint.
Okay. Well, that's impressive. So you're able to drive the unit in there, drill multiple holes, relatively no mess, and then essentially offload 80 to 90% of their heating and cooling requirements.
Yeah, above 90%. Yeah, for
Above
sure.
90. Wow.
Above 90%. We can, on a lot of the buildings we've already designed, we like to keep it to 95%
Mm-hmm.
because having that boiler it's good practice as a backup, but it's economic. So trying to chase the last 5% of carbon emissions is not an economic venture. If I could do 4 times as many buildings, if I just leave that 5% sliver in there, that makes more sense for trying to transition the energy economy into a decarbonized solution. So there are some clients who want 100%, and we can do that, but we tend to, for an optimal solution, life cycle cost basis, it's much better to keep that boiler, and that allows us to play the games we need to with the tariff structure. You're in the middle of winter, you got a really high electrical peak price in Alberta. Well, don't use your heat pumps then, use the boiler then. And
Mm-hmm.
when you're charging, it's even better. So the trick in Alberta was to use the spot price, because in Alberta, the spot price varies from free, basically zero cost for electricity, to $1,000 a megawatt hour, and they're planning on increasing that. So
Hmm.
it's like $10.
But does everybody have access to that market though? Or you have to
Large
be, I think
buildings
you have to
would.
be a special player with special access to get that grid
Any
pricing.
large building can choose that. So
Okay.
the tariff structure in Alberta is the D310 is one of the providers. So our buildings for this scale of solution are typically 100,000 square feet or larger. If you're
Okay.
smaller than that, then you have the problem that you just mentioned, and then we have different solutions. So we're working on projects for a bank, so a 5,000 square foot bank, but that would be more the small scale and not what ThermaCity Energy would do. That's where Ada Energy Solutions would get into it. We are looking at it at ThermaCity Energy. We're trying to solve that problem, but the small scale problem is a different nut to crack. And
Okay.
so we tend to focus on large with this system.
Yeah, so we'll save the small scale, and even I'm thinking the Drake Landing we'll save now for the Ada conversation because it's more residential focused. On the big scale, 100,000 square foot or bigger, in our work we come across hockey rinks and
Yep.
conference centers. You're looking at condo buildings, malls, office towers, factories. Certainly, some factories are
Industrial.
way bigger than that. So do you have a specific target market? Do you have markets you want to avoid? Do you have provinces where this makes more sense than others? What are you seeing?
Yeah, that's a great question. I mean, and this is something we've studied at depth. So there's 4 target markets that we approach. We have the buildings market, which is 40% of all of our carbon emissions come from building heating and cooling. So that is our largest market, but not necessarily the best market for us. So district scale, like you mentioned, the large campuses and community scale deployments. That's district energy, heating and cooling. So that's the second market. And then data centers is the third market. So data center cooling, a completely different problem. Now you're not trying to heat the building, you're trying to cool this data center, and we try and unlock additional compute to reduce that data center's cooling and to do it waterless. So our solution is completely waterless, no impact on taking water out of the river, or taking water away from residential communities. So that's our solution for data centers.
That's
And then
huge.
finally, that is our biggest potential market.
A quick side note, shout out to my daughter Hallie, who is currently, and a lot of her kids of her generation are currently very anti AI. As much as they're into Roblox and other video games and things, they're all taking on this water issue as like existential for their generation, and so they're not too happy with what they're seeing with AI data centers at the moment, mostly related to water. So very interesting that you mentioned that.
Well, it is a big social acceptance problem, and part of that is some misinformation. On like, I have the same issue with my son here. They are concerned that every time they do a poll on an AI, it's worth 3 glasses of water, right? And
Yes, there's a
that would
lot
be
of things
true if you're
getting
using
batted
water
around like
cooling.
that.
Yeah, but it doesn't actually apply to the data
Right.
centers. But with our solution, not only can you have the reduction of water, we can actually tie, and here's our best case. We tie the data center output heat. We store that heat all year long, and we use it directly to heat a district energy network. That's our number one best use case, and that solves all of your
Mm,
environmental issues. You flip that environmental issue into a positive, and now we're eliminating natural gas from a heating problem from the waste heat out of a data center. That's our best solution,
right.
and that we could do at the industrial scale. So that's our fourth market is industry. So
That is very interesting. We the stories that I've heard coming out about data centers, there was one where they're close to residential, was they caused major problems, like in the States where they were pulling all the water, and then the homeowners down in the
yeah,
neighborhood, these small
couldn't even have
towns where
water.
they get some
Yeah,
tax break or something, and then these homeowners are like having empty wells basically and not having any water, so they're pissed off. But then we haven't really talked a lot about co-locating data centers in a way that is mutually beneficial.
right.
Recently, I was discussing with somebody that I thought there's merit in co-locating with a greenhouse and taking the heat off the
Of
data
course,
center to heat a
that
greenhouse. But we're not making those connections yet, and I love the way you're putting it as district heating layering to it.
yeah, district heating, greenhouses, a great application. Whatever we can do to use that waste heat, but do it without using water, do it with having the smallest impact on the grid or your power generation as possible. That's what this thermal energy storage unlocks for us. And so that fourth market is industrial scale. So we're looking at grain drying. We're looking at chicken barn heating. We're looking at these applications where now we've got a really good tie into a large heating load. And it's some of the places in Canada, this is something that I only discovered. I grew up on a farm, so I know a lot about these industrial cases, industrial agriculture. And yet in Manitoba and Ontario, they don't use natural gas to do their grain drying. They use propane. It's at 5 times the cost of natural gas. They just don't have the network that we have in Alberta or other parts of the country. And so those are use cases where you can really gain an advantage by storing this heat from the summertime, using it when you need it, that peak fall period or winter for heating your barns, all those kinds of applications. Mine heating is another application.
So to store, let's dig into that for a second. So to store the heat from the summer, let's say for a grain drying application, are you um, are you pulling off of like an air to water to glycol heat exchanger, heat pump, or something like solar wall or a solar thermal plate collector? What are you using to capture that and then pump it into the ground?
So, depending upon your tariff structure and what's available in that province or that location, you're exactly right. We would use air source heat pumps to
Okay.
drive that heat into the ground. That if you've got a variable tariff structure, when you get really low cost electricity or zero cost electricity, and we're going to get more and more of that, the more renewables are developed, then that's the simplest because you need that heat pump anyway to take the heat back out of the ground. So we use a dual source heat pump. It could do both take heat from the air or it can take heat from water. And that's how we put it into the ground in the first place. We use air to water, and we take it out. We go water to water, take it out, meet the load in the winter. So that's one source, but we use whatever source
Hmm.
is available. We might use photovoltaic thermal or the solar wall, like you discussed. Whatever's cheapest.
Yeah, because I wonder, you mentioned that the big building operators have access to the wholesale markets, the spot price. I'm wondering, would a typical farmer with a grain drying operation have that same access? And also the time of day when you might get $0, incremental power on the grid. Does that line up with when it's hot outside, or things of that
Well,
nature.
and that's the magic of it is we look at exactly what you said, the time of day or what it really is, the ambient temperature. How hot is it outside and what's the price of electricity? And that's
Yeah.
our exact formula for doing that. We take that and we take it with the heat pump's efficiency curve and we say, when's the best time to charge this field? And that's how we do it.
So do you guys have some software that you've developed or something to manage that, some controls or some kind of intelligence?
We have a very sophisticated control algorithm that looks at the weather. It looks at the predicted weather forecast and it says, oh, it's going to get cold. We better charge up, get ready for that cold snap. Or it looks like tomorrow's price of electricity is going to be lower because the price of electricity is quite predictable.
Yeah.
And you can, when you're looking at it instantaneously, of course, if the price is low now, we will run now, but we know 24 hours ahead when there's going to be a low price of electricity.
Wow. So you're pulling weather, real-time weather, forecasted weather, real-time
Forecast.
spot prices, forecasted spot prices, and your system is making automatic decisions.
That's correct. It's basically AI. So we use AI to analyze those forecasts and make the determination. It's really machine learning. It's a form of AI. That's how we build our control algorithms. But we've been working on that. Well, I've been working on it for over 20 years, and that's exactly what we've done. So in 2008, I worked on weather predictive forecasting for heating and cooling controls for these kinds of hybrid systems.
That is so cool, James. I do geek out on this. I don't know if everybody will appreciate it, but I certainly do, especially if you're stacking like your tech stack, if you will, in terms of the different devices from natural gas to electric, heat pumps, solar wall, plate collectors, and trying to ride the line of which one to use when, based on what's going to be the cheapest.
To figure that one out.
Yeah, I mean, that is not an easy task. But
no, and you have to do it in a way that is operable, that's maintainable, and is still cost effective. So we have to make some sacrifices on efficiency to make it easy to use for the operators. So what we try and do is bundle all that controls in, and we include in all of our projects 5 years of monitoring and optimizing the system to ensure it's operated as per the design intent, it's achieving the design intent, and there's even an additional 10 to 15% optimization. Once we start the system, we take that data back from the system and we recalibrate our model and our controls to optimize the
so
output.
You've got specific learning for that operator in their building, and then you've got kind of aggregated learning for your whole portfolio of projects everywhere.
And we continue to learn because every time we tackle a new problem, it's a different solution, a different answer. So it's a real engineering challenge, but we've built some tools that help us with that. And just before this meeting, we were working on the next generation of those tools. But yeah, that's how we do it. I wanted to talk about scale though.
Yeah.
So, I mean, you mentioned Drake Landing, but Drake Landing was actually meant for larger scale. It was a pilot of commercial small scale district heating, but it's meant to be larger. And in fact, when it gets larger, even 4 times the size of Drake Landing, which if you consider it is still small, Drake Landing was 52 homes. So imagine 200 homes. That's not a big community. But when you do that, the improvement on Drake Landing's design would have been 35% lower life cycle cost. On our design, it's 1/6 the cost of Drake Landing.
So Drake Landing's been around for 20 years. Are we seeing, I'm not very familiar with this, are we seeing developers like your Mattamy Homes guys and those folks, are they starting to buy into this now? If so, why? If not, why not?
So in North America, it hasn't been as much because our cost of energy has always been the challenge. Like this Alberta market is typical. It's higher electricity costs, lower gas price. But in Europe, they are doing exactly these kinds of designs where they combine the technologies, deploy at the district scale. So there's a site in Norway at the University of Stavanger in Norway that I went to, and they're doing their entire campus with this. And they do the similar combination of technologies to kind of save a little bit on use photovoltaic thermal, you've got a lot of waste heat from the backside of the PV cells going in, and you've got summer low cost electricity, and they put that into the ground and then extract it for the winter heating loads. They do it in Poland. They have a huge system like ours, and then on top of that, they put a pit storage tank, a large water tank that they store the heat in for short term. So it is happening. In the U.S., they did borehole thermal energy storage on one of their military bases in Albany, Georgia, and they analyzed the first one with Geoexchange, just low temperature heating cooling, and then they did the storage of cold, and they used dry cooling fans to store the cold in the winter and then extract it in the summer. They did the first analysis and said, you know what, we're going to do the other 5 sites just like this.
Wow.
Because it was saving them 30% on capital costs and 30% in running costs for the year to use this storage method of doing it. So it's happening in North America. We're still trying to educate and disseminate. I was just at a conference in Colorado where they're looking at it for data centers, and it's all across the spectrum, from university academicians to researchers at the National Laboratory of the Rockies to data center developers. They're there. Bitcoin miners were there saying, how could we make this more environmentally friendly and cost effective? Because Bitcoin miners are all about making money.
Because they're running chillers and AC units to cool off, like fans, and just
you have to run
inductive loads
chillers to do that. And what's happening there is they're raising the temperature that they run their chips at. So now the chips are somewhere between 30 to 50 Celsius for the cooling supply temperature. That's not what comes back. That's what they send to cool the chips. Well, that's a very useful temperature to store in the ground and use for district heating or to heat a building. So we are looking at co-locating data centers. We did an analysis for a university campus in northern British Columbia, and a 5 megawatt data center could service 85% of the carbon reduction for a 20 megawatt thermal load in the winter. So that kind of synergy is where we really get the advantages.
Yeah, absolutely. I'm just thinking about, which buildings are, like, whether you're focusing more on new construction or retrofits. So you've mentioned both. Is there a scenario that's just easier to implement? Does this make more sense on new projects or on existing buildings?
Well, we're pretty agnostic towards that. We'll do whichever one. On the new buildings, there's some challenges and advantages to our drill bot, because what we can do on a new building, if you drill Geoexchange, you have to wait 3 months for the drillers to complete drilling it. They make a horrible muddy mess in the bottom of your foundation of your building, and then you're trying to work around the other trades. Or you could use our drill bot, wait till you're on the 11th out of 12th story of your building, then you drive the drill bot in underneath the parking structure, and then you drill your holes for your field. So that's on a new build, and that helps with the construction timeline. It helps de-risk the project, because what if that building never actually gets built? You've already spent all the money on your bore field, but now you don't have enough money to finish it. So financiers are seeing this as a de-risking method for the new build. But for retrofit, there's almost nobody out there who can go into a parking structure and drill in a 2.2 meter height. There is one other competitor who's just working on their prototype drilling rig. They're using a slightly different method. It's called Dig Energy, and they will be able to go into a very small height and attract a little tiny rig and try and drill. I don't think they use the coil and tubing technology, but they could still do that with their method. It's a slightly different method, but that's what it takes to do retrofit of these larger buildings. So
what about a hockey rink? Would they be able to utilize this system?
So rec centers, so if you've got an ice rink and a pool, you've got this synergy between, I want to cool the ice, but I want to heat the pool water.
Right.
But in the summertime, sometimes those rinks shut down or they're not operating. And so now you've lost the time. It's not synchronous in time. So our thermal energy storage creates that ability to shift the cooling of the ice rink, and that energy has to be rejected somewhere. Normally we throw it to the atmosphere. But what we want to do is store it in the ground and then use it for that pool heating year round. This is a perfect example of where thermal energy storage is the right solution to synergize those different load profiles and flatten them out. When we do that, we reduce that grid requirement. So we reduce your grid energy, your grid connection, and we make both sides more efficient. So yeah, recreation centers are a perfect example of what
And
we
in
can do.
that case, this is another layer to the existing heating and cooling stack of the building, where you're now, let's say they've got chillers or boilers for their hot water for the ring for flooding. You're pulling heat off of those systems and storing that for use later, or you're eliminating those systems entirely and now getting your heat out of the ground. And
We would never eliminate the systems, but we would do what you said. We would pull that heat and save it for later, or we pull that cold from the summertime and save that for later in the rec center scenario. So if you're summertime and you only have heating the pool, well, you're creating a cold storage that you can use to do the ice making later in the winter. So that's what the thermal storage helps with.
So just kind of building on that for a second, and forgive me here because I don't intend this to be a gotcha question. I know that in sort of the southern areas of Canada, sounds like a no-brainer opportunity. When you start to get north, we run into permafrost problems in a lot of communities where their buildings are slowly melting the ground beneath them, and then their foundations are shifting, and they end up having to install thermosiphons to try to keep the permafrost frozen so that their architectural and structural supports don't get compromised. Have you looked at how this technology could or could not be utilized in those environments?
So that's a great question. And we actually have a similar problem down south, but your permafrost problem is one of the most challenging, but we have a solution for it. So we actually have a patent pending solution on the upper part of the bore field. We can insulate that bore field, much like your thermosiphon. So back in the day when I worked on gas pipelines, they have that problem. And if you have your pillars in the permafrost and you melt the permafrost, you'll sink the whole pipeline. So the same idea here is like those thermosiphons you mentioned. We keep that upper layer of the bore field frozen in permafrost, and then we only heat exchange below. So we would have 30 to 50 feet of the upper layer completely insulated so that we're not causing any permafrost damage. In fact, we can make that upper layer thermosiphon protected, just like you described.
So you're insulating the pipe section,
We
or
insulate
the whole
the heat
field,
exchanger. No, just the borehole itself. So
Yeah.
where the heat goes down into the ground in the summer, that would melt your permafrost and sink your building.
Yeah.
Now we probably wouldn't put one of these, the first one, underneath the building. We put it outside to make sure this permafrost solution works. But
Yeah.
if we insulate the borehole at the top and actually put in a thermosiphon, just like we would a pile for supporting a pipeline, you would freeze the outside of it, take the heat that you were freezing, put that into the borehole in the insulated middle part, go down to your depths and store your heat at the depth where it's not going to cause anything to sink or swell.
So from a top view, your schematic has kind of concentric rings like a tree, and one of those is kind of cold and one of them is going to be hot, and you're going to have separating from the
right around the borehole
environment.
That's a great description of it. I can actually play a video of this, which would probably help everyone to understand what it is we're doing. So let me jump to that, see if I can do this. Okay, I don't know why it says I can't share slides right now. Let me try this. There we go. So here's a video. This is our explainer video. And tell me if I can make that bigger here, if that works. Let's see. How about that?
Great.
Okay, so this is the building example, and we'll get to your question on permafrost, but there's collectors up there. Those are photovoltaic thermal collectors. So there's PV cells on the top side, and then there's fins on the backside that collect heat from the backside of the PV cells and from the air. So PV cells can get up to 70 Celsius in the summer. We don't want them that hot because they're inefficient. So we run glycol through there and run it colder than the air temperature. So we get heat both from the sun and from the air. And we take that heat in the summer and we'll store it in our
And then
ground
your
field, our
solar
bore
PV
field.
is actually generating more electricity too.
It's about 15% more annually. Good catch. So passively, just circulating our glycol through there, we can charge the field at the beginning of the season because it's cold. It starts at 5 degrees Celsius. That's intentional to avoid having glycol in our field. We warm it up to about 20 degrees Celsius, and you can see the field start to warm from the inside out. That's the difference between Geoexchange and borehole thermal energy
Now you
storage.
mentioned passive. Is that literally because of the temperature delta? It's creating its own current, or you're just saying just still pump assisted?
Well, there's no heat pump when it's passive. And then when it's active, we turn the heat pump on and we'll put cold,
But it has a circulation pump, or
just a circulation pump.
okay.
That's what we call passive. So circulation pumps, you can get about 30 times the energy out of the source. So 1 unit of electricity would give you 30 times the amount of heat. When you're running a heat pump, you get maybe 4 or 5 times the amount. So that's when you're active. So actively, we charge from 20 Celsius all the way up to 45, 50 Celsius if we need it. This is kind of our optimal 45 Celsius. Now, at the beginning of the season, 45 Celsius, that's enough to heat your buildings. So we passively discharge. We just run a circulation pump, and it takes the heat out of the field until it gets too cold outside and we have to have more than 35 Celsius to heat the building. So then we'll turn it into active mode on the heat pump, and it'll suck the heat out just like a Geoexchange field would, but it sucks it from the outside in. And we save that store at the core for that peak of the winter to make it through that. And then the year cycle is completed. We've done a full year cycle.
So this really offers a long duration thermal energy storage solution that, if you were to stack this up against, let's say, batteries, lithium ion batteries, it sounds to me like no contest. But you tell me.
It is no contest, and but they're different purposes. So batteries, lithium ion batteries, are really good for the 4-hour duration, trying to meet your peak load. We're storing over a season. The cost of lithium ion batteries somewhere in the range of $250 to $500 a kilowatt hour. We're at less than 50 cents a kilowatt hour. So with that cost, we can get away with doing seasonal storage. I mean, on smaller systems, it might be $4 a kilowatt hour, but you could see it's still far, far less than 250. But you're storing electricity, we're storing heat. So your $250 is really worth a quarter that price-wise.
As we continue to decarbonize and fuel switch away from natural gas towards electric heating and cooling, this does become more and more relevant, more and more cost effective, and a real apples to apples comparison now, because even though it is heat, it's still more and more electrically generated heat.
Not only that, but if you did the electrification of you switch from natural gas to electrified heating with just Geoexchange, you have to run your heat pumps at the peak hour of the winter season. In Quebec, in Halifax, and soon in Ontario, you already have the peak of the grid happening in winter. So there's 2 peaks in Quebec. They happen at near 8 in the morning when people get up, and around 5 or 6 when they get home from work. But it's winter, not summer, that drives the grid peak. What we're doing with the thermal storage is allowing us to harness the existing capacity of our grid, the wires, and we could decarbonize 25% of the built environment before we had to upgrade the grid at all. That's what the thermal storage allows us to do. Think of that savings. If it's $40 billion to upgrade the grid to try and do partial electrification, we can postpone that, take the first 10 billion, don't spend that at all, and harness the existing grid. That's what grid friendly means.
So are you working with utilities to see
Absolutely.
This value prop? Certainly a lot of them do invest in rebate programs, incentive programs for homeowners, commercial business owners, to do the energy conservation work, and then we'll give you a percentage of it back because it's cheaper to save a megawatt hour than it is to generate a new one. So where are you in some of those conversations now?
Yeah, we're already working with the major ISOs across Canada and into the US. So we've already met with Toronto Hydro and the ISO in Ontario to say, they asked us, what is the best way to do thermal energy storage and harness that to be grid friendly, and what kind of funding program would make sense? What are the barriers? How much cost? Where would we, what do we pay for to make it work as a program and make sure there's uptake? Because if there's no uptake, if there's not enough players out there doing it, there's no point having an innovation program. So they've asked us, and we'll continue to talk with all of the major ISOs and discuss the new tariff structures that identify and value the impact we have on the grid, so that we can deploy the most cost-effective decarbonization, energy transition, and be competitive on the world market. That's what we need as a country, and that's what the world needs to decarbonize and save the planet.
Yeah, well, it certainly sounds to me like this just gets better with scale. So doing stadiums and massive towers and massive factories really has like a knock-on ripple effect to everybody downstream, to everybody in the neighborhood, to those factories themselves in terms of their profitability, to the grid in terms of shaving the peaks, allowing them to not have to get into these premium prices as often for everybody down the line.
I think it's good to talk about scale. If you look at it, 100,000 square foot multi-unit residential building, one of those, a set of chicken barns at a large agricultural facility is worth 4 times that. Grain drying facility at the elevator scale is probably worth another 4 times that. And if you
Really?
jump to the right, yeah, it's huge. It's huge, our grain drying. But then we take a data center. We're building hyper data centers at a scale unprecedented in history. So a small hyper data center is 100 megawatts. That's worth 20 grain dryers. So you're talking 100 times what the energy potential is from doing one building. If we can harness that and synergize with data centers, we can eliminate our effectively the impact of our heating by launching into this next generation. We're really into another one of those technology races with data centers, and we need to have that to stay competitive. But we want to do it in a way that's not hurting people, not impacting their water, not impacting the price of power on the grid. And this is the way to do that in part, even if they're isolated. So there's a big data center plan for Grand Prairie in Alberta. You may have heard of it, with Mr. Wonderful. It's a 7 gigawatt data center,
Wow.
7,000 megawatts. That's half the Alberta grid in one place. So if you don't do that in an environmentally responsible manner, you're going to have huge impacts. And with these waterless cooling systems, that's the way to do it. And it really harnesses both your heating and your cooling. If you can then tie that to district heating, there's data centers planned all around major centers, but typically outside the major center. But there's no reason we can't use it for district heating
Yeah.
or
Well, what it
greenhouse or
really sounds
industrial.
like,
Yep.
there's a kernel of an opportunity here, just in the same way that they do tech innovation parks or university campuses. I feel like if a community wants to do a data center or a province wants to do a data center, the land use zoning and planning should almost be like concentric rings coming out from the data center, because you can then feed housing, businesses, factories, greenhouses, grain dryers, like all of those things off of that data center. So instead of having it be this albatross that people don't want in their backyard, it now becomes the catalyst of what they do want because of
Yeah.
everything else it does.
Instead of the NIMBY approach that is a right way of addressing data centers that aren't environmentally responsible, you're talking about, please, in my backyard, I want it because I can have a 360 acre greenhouse that's fed the carbon dioxide from the power plant that feeds the data center, and there's no water consumption. In fact, you've reserved the water for growing the food that the communities need, and then at the same time, you're heating the entire town that's nearby. That's what we want.
Yeah, so certainly if there's any mayors or chiefs listening to this, maybe consider it. Now, obviously, I don't have a horse in this race, and I might be missing something or have a blind spot in terms of data centers because obviously there's a lot of controversy over them right now. But as a mitigating solution to try to reduce the negative impacts of data centers and turn those negatives into positives, this sounds extremely promising.
And we can even do it at small scales. It doesn't have to be at the hyper data center scale. You
Mm-hmm.
take a 400 kilowatt data center and you put it in a warehouse facility. So one of the hardest problems we had was a warehouse facility in Alberta, cheap natural gas, expensive electricity, and heating only, no cooling at all. So we had no way to balance the geoexchange field, and even trying to do free or low cost air source heat pumps. We had to buy that. We had to buy the electricity. We had to charge our field. We couldn't make it be net positive. Now throw in a small 400 kilowatt data center or Bitcoin mining facility, and we not only have solved it, but we can actually give them a discount against their current business as usual utility case. And at the same time, the data center gets a free cooling of their data center. So these are great solutions that apply across various scales.
Incredible. A couple of minutes ago, you touched on solar fields and pulling the heat off of them in Europe. Is that also something that can be retrofitted? Because I know there's a lot of very large solar fields in Alberta, for example, that are going up. Is there a way of going in afterwards and pulling the heat off of the back of them so that those solar farms can be 15% more efficient? Or is this just on these PV thermal combo units where you're starting out the gate with the system in place?
I don't think it's practical. I don't see a way to go back and do, because those collectors, those modules are all a different technology, and there's no way to strap on or straddle any kind of heat recovery system on the existing ones. However, we are building more and more megawatt scale PV systems, and there's no reason that couldn't be done with some kind of PV thermal technology, whether it's a solar wall that uses standard conventional collectors, or whether it's a PV thermal specialized collector where we run glycol through the backside of the panel. I see that as a great opportunity. That's another heat source. We're talking 100 megawatts of PV. 100 megawatts of PV is 400 megawatts of heat. So just consider your PV cells are only 25%
And right now that's all
efficient.
$0
Zero
being valorized.
You have to fight the heat because your cells get too hot.
Right.
Really convert it
right.
into
So
something
I'm
useful.
curious, just thinking out loud here, how much more expensive is a PV thermal panel that's got the system on the back end? It feels intuitive to me that if you're 15% more efficient, that alone is going to have a payback at some point. Now, depending on the premium of adding that glycol loop and the extra components on the back end, how fast that is, I couldn't tell you.
Yeah, right now the cost is still high on that technology because relative to PV, it's still new, but it's not new. It's 30 years old, but they haven't done the scaling and the cost reductions. If you watch PV cells drop from 2010 to today, it's dropped by a factor of 10. So that's a pretty incredible drop. We can see that if you get up to scale on these PV thermal collectors already. I mean, we use a French model right now. It's called Dual Sun, and it's about 2.2 times the cost to install as a regular PV collector. But there are Chinese versions, very simple, straightforward, that are only 80 cents a watt more than conventional PV collectors. So that's pretty reasonable.
Well, and if you're would you, how close to that 4x thermal generation are you able to capture with this 80-cent premium?
Yeah, so for 80 cents premium, you're basically getting an additional 2.5 times energy. It's thermal energy, so it's not as valuable as the electricity. But on top of that 2.5 times of thermal, you get that extra 15% electrical as well. So that really helps make the economic case.
I mean, you do you. I'm just thinking from talking to the utility companies, that are having these peak demand issues and these kind of load balancing issues, and all of that, that seems to be a decent fit for where they might see value in supporting at least a pilot scale of a system like that to see how much of a difference that can make to their operations of the grid in that region.
The key to unlock that is to combine that thermal storage element and two thermal storage elements. You want to combine heating and cooling. Consider your PV array operating in winter. Well, it's a huge array that could collect cold. We can store that cold and use it later. So you would want to combine that PV array with heating and cooling district network. And we have some heating and cooling district networks, but we need to develop more of those to unlock that scale. At the same time, I'm agnostic. So if I can do a single large building without running district energy piping that's very expensive, then I'll do that.
Right.
I'll do whatever's the cheapest, best way to
Well, and it even
decarbonize.
that example from a few minutes ago of the data center in the middle and all of your other buildings around it, you could kind of do the same thing just with your solar thermal,
With your solar array.
PV thermal array, gigawatt, whatever, megawatt, whatever in the middle, and all of these uses around it as well. And maybe people like that more.
Yeah, those are huge. It's hard for people to imagine what 100 megawatts of heat can do. So 100 megawatts of heat from a data center. Well, if you have a 100 megawatt PV array, I said 2.5 times. So that's 250 megawatts of heat that you're going to collect. Now, it's not all year long like a data center is, but a 100 megawatt data center will do a 360 acre greenhouse.
I mean, my goodness, it would almost
That's
even be
pretty big.
worth it. I could be wrong here, but for a municipality or a provincial government to subsidize that difference in cost, to just have that at the ready to attract businesses, to attract users of heat, whether that's a brewery, a grain dryer, a school district,
that's the level of planning
whatever
we need. But consider, I mean, they don't even know that thermal energy storage exists at this scale. They don't know about the combinations of solutions. So there's an education and dissemination, which is exactly what you're doing here. And we need to talk to those government officials. And that's part of our plan too, is to issue white papers and policy documents to the Minister of Energy federally and provincially so that they can understand what the opportunity is and what this thermal energy storage, if we want to lead the world, we need to unlock thermal energy storage and the technical ability to deploy it. And your examples are exactly what should be done as demonstration projects and rolled out. And so we are working with that. We are working with Horizon Europe. Canada is a participant in Horizon Europe. They issue funding at 9 million euros per call, and we're already pursuing multiple calls to do thermal energy storage at industrial scales, at urban, dense urban environments, and deploy exactly the solutions we've discussed inside cities to solve our decarbonization problems and our energy transition.
Well, this is a fascinating topic, and it reminds me of like Canada's strengths, right? When we play to Canada's strengths, people sometimes say, "Oh, I want to move to Florida because it's hot year round." "Oh, I want to move so and so, it's too cold or it's too this." But at the same time, the average Canadian actually, I think, loves our seasonality. They love that we have the 4 seasons, that we have the spring and then summer and then the beautiful colors of fall. And then we have these amazing winters. And like, we need to figure out ways to heat and cool our buildings that really play into our strength in spite of climate change, because we're still in an advantageous position relative to a lot of other parts of the world as climate change continues. And like, I see this as a great solution for this country. So as we want to build Canada strong and build better and all the different slogans, figuring out a way to take full advantage of our seasons just seems to be a perfect fit for Canada.
And what we've done here is we're also taking advantage of Canada as an energy giant. So we're an energy giant in the oil and gas realm. We've actually transferred two technologies from oil and gas into this heating and cooling space, into data center cooling. And we're taking our knowledge, our know-how, and we can disseminate that and deploy it worldwide. So we can be the leaders in the next generation of energy transition. And that's what the technologies are that we're talking about. And it's not just technologies. You have to have the engineers, the trades to be able to deploy these technologies. So this is job creation. Think of how much it takes to build a district energy network, or what it takes to do the mechanical systems for these complicated energy systems. Heat pumps, that's going to be more work for our trades. In fact, we don't have enough trades to install all the heat pumps that we need to install. We have to have training programs to add into our technical institutes and get more people employed doing that. And guess what? AI is not going to take those jobs away. They're going to create jobs for those people. You can't have Claude Code install a heat pump.
Right.
He's not going to do it.
Well, as someone who was born and raised in Ontario, lived in BC, lived in Alberta, I appreciate, and I love the Maritimes, I appreciate all of Canada and all of the things that we go through. And sometimes I do think Alberta gets a hard rap because we need Alberta and we love Alberta. And it's not necessarily fair to say you guys, can all lose your jobs while we switch over to something else. Whereas this allows, I think, for a very nice soft landing for a lot of those drill rig operators and things to be able to use those skills and use those technologies to apply it to something that's got a very bright future. So with that, I think this is probably a good place to end our chat for today on this topic. There's so much more we could cover that I think maybe we'll have you back and go deeper on some other case studies perhaps. But you've given us a genuinely useful tour of what's possible underground and above ground as far as capturing thermal heat and storing it, playing to the natural seasons of Canada. For those who want to get more information, maybe want to reach out to you, what's the best way to get in touch with you?
I'm on LinkedIn, and our company website is thermacityenergy.com. That's the best way to reach out to us. And we have lots of tools and information, white papers and other things on our website, and you can learn more about us. Our headquarters is in Toronto, and that's where our current drill bot is sitting there. It's on demonstration at the moment. And then I'm based in Calgary. We have offices or personnel located in Quebec as well. So that's our breadth, and you can reach us there at theenergy.com.
James Bererton, it's been a pleasure. Thank you so much for joining Energy InSites. And we will stay tuned for part 2 of our doubleheader, which we will be starting in a few minutes.
All right. Thank you very much, Kevin.
Thanks, everyone. Bye.